Okay, so hi everyone, my name is Marina and I'm currently a postdoc working with Heather Segla at the University of Warwick. However, in this talk I wanted to show you two of the projects that I did mainly as part of my PhD while I was at the Institute of Space Sciences, so before joining Heather at Warwick. And the two projects are about how stellar activity affect the stellar spectra, and yeah, we'll talk about two projects. So in the first one, I will show you a study that we did on a set of activity indicators to assess their behavior, and then the second project we try to implement that, the knowledge that we learned in the first one, to try to do computer velocities following a line-by-line approach on some active stars. Okay, I hope you see the second slide. As we've been talking these days, you've seen that there's a lot of different methods that use different activity indicators to try to assess how stellar activity or stellar variability affect our observations, our spectra, and our velocities. So here I'm just showing you some of the most standard and most used spectroscopic activity indicators. So I have on the left a cross-correlation function. I will be calling this CCF, and here I have some parameterization of its profile that trace activity, such as the full width at half maximum, the contrast, or some different parameterizations of the bisector that trace the asymmetry of this cross-correlation function. Then I have in the middle the chromatic index. That's just a measurement of how the radial velocity changes as a function of wavelength, because as you know, the stellar activity is chromatic, so these indicators just measures the slope of this radial velocity with the color. And then in the end, I have on the right hand side, I have a plot of some stars in the region of the H-alpha line, and this is a chromospheric line that's also been shown to trace stellar activity. So I'm going to be using these indicators in the work that I'm going to show now. So to start with, I just wanted to show you some of the data, how the data that we use looks like. So this is CARMENES data. So CARMENES is a high-resolution spectrograph that observes in the visible and the near-infrared. I'm just going to be showing data of the visible channel here. So this is a YZ-CMI. That's a very active star. It shows a very nice and clear signal at its rotation period. So I'm going to be showing many plots of this star because it's nice to analyze. So on the left-hand side here, I have plotted the time series of the radial velocities of the star and three different indicators. So in this case, I have the full width at half maximum of the CCF, bisector of the CCF, and then the emission flux of the H-alpha line. Then I just phase folded these quantities at the rotation period of the star that we know is of about 3 days. And then the plots here at the center are just simply the correlations of these three different indicators with radial velocities. I just wanted to quickly show these correlations because we see that some indicators seem to show correlations that look like linear. I know that we've said before several times that correlations are not linear, but at least for some indicators they kind of look linear. So in this case we have here in the middle the correlation of the bisector with the radial velocity, and I have written down here these R values here that are the Pearson's correlation coefficient. So this one is almost perfect anti-correlation, close to -1. And I wanted to show here the full width at half maximum too. We've just seen this in the previous talk, and this one, the correlation, if you look at the values close to 0, so that would indicate that there's no correlation. But if we look, for instance, at the phase of this point, so I've color-coded the different data points that I have here with the phase of the star at the stellar rotation period. And if we look at the different colors, there's some kind of evolution, there's some kind of loop with the colors of the phase, and this is probably due to the fact that there's some kind of lag between the two indicators that we have also seen before. So I just wanted to highlight that. Then finally, at the right-hand side of these slides, I've just computed the periodograms of these 4 different quantities. So in this case, for this star, I wanted to show that 3 of the indicators, so radial velocities and the full width at half maximum, the bisector of the CCF in that case, show a very clear and significant peak at the stellar rotation period. That's the peak you can see here. I've highlighted where the rotation period is in blue. And I just wanted to show that in contrast, other indicators such as the H-alpha line here show nothing significant. There's some kind of peak that you can see here at the rotation period, but it's not significant. So this seems to indicate that this indicator in this case is not tracing activity as well as the other ones for this star. And I just wanted to show you another example, same kind of data. Another star, in this case, is CN Leo. It's a medium dwarf, also quite active as YZCMI. And in this case, I'm showing you the velocities for width at half maximum of the CCF, chromatic index in this case, and the H-alpha line. And for this star, things look a bit different. So in this case, only the velocities and the chromatic index show a very significant peak at the stellar rotation period of the star, but none of the other indicators show anything significant. So that was our motivation for the results that I'm going to show you. So we did some that I'm going to show you now. So we did this kind of analysis, periodogram analysis, in a set of about 100 M-dwarf stars. I'm showing you the sample that we use here on the left plot here. So here we have all the stars that we have analyzed, and I'm plotting them as a function of their activity. So from less active to more active on the y-axis, and from more massive to less massive on the x-axis. And here on the right, I'm just showing you the different spectroscopic activity indicators that we've analyzed. So the velocities that we derive from the standard template matching technique, the standard pipeline that CARMENES uses, then chromatic index, another indicator called differential line width that measures, it's a kind of a measurement of the width of the line, so it's somehow related to the full width at half maximum of the CCF. Also the three indicators from the CCF, and then the visible range of the CARMENES arm covers two chromospheric lines, and I'm going to be looking at these. So these are the H-alpha line and the calcium infrared triplet. So the kind of analysis that we did is mostly what I just told you. So we took the time series of all these stars and all these indicators, computed the periodograms, and looked for signals that we could attribute to the stellar activity. So to do that, we look for signals at the stellar rotation period, the harmonics of the stellar rotation period, and the one-day aliases of these quantities. And if the stellar rotation period was not known, we look for a significant peak in more than two indicators. And if we found that, we would attribute those signals to the activity of the star. So then I'm going to jump now to the results that we got. So the idea was to get some kind of like an overview of how these indicators behave on different stars. So on the left plot here, I'm showing you again the sample of stars. So as a function of their activity and their mass. And I've divided the sample into 4, depending on how active they are and how massive they are, to be able to extract some results. And on the right-hand side, I have 4 panels here, which look very chaotic, but I'm going to try to explain them. So the axes on these plots are the same ones as the axes on the left. So I have the activity level of the star and the mass of the stars. The points and crosses that you can see around here in gray are the different stars of the sample. The bins that you see here are the same bins as on the left. So depending on how massive and how active the stars are, I've just grouped them into 4. And then the colors of each bin tells you how many of each bin tells you how many stars in that specific bin show a signal that we can attribute to activity. So light colors mean that most of the stars show a signal, and dark colors means that almost none of the stars show signal. And I have 4 plots for 4 different categories of activity indicators. So we saw that some activity indicators behaved in a similar way, so I've grouped them to be able to extract better results. So if I'm going to start with the plot on the top right, so here I have the results that we got for the analysis of the chromatic index and the bisector of the CCF, which behaved in a very similar way for most of the stars. So in this case, we see here that most of the stars at the top of the plot here, so these are the stars in the high activity regime, seem to show a signal. And most of the stars in the low activity regime, so the ones down here, these are like dark colors. So most, in this case, most of the stars tend to not show a signal. So this would tell us that these indicators are good in assessing, in finding activity signals for active stars, but not so good for stars that are not that active. Then if you look at the plot below that one, I have the results for the chromospheric line. So I've just grouped the H-alpha line and the 3 lines of the calcium infrared triplet into one. And in this case, these indicators seem to behave kind of in the opposite way as the chromatic index and the bisector. So for the least active stars, these indicators seem to trace activity quite well, and not so well for the stars that are more active. Left of this one, so bottom left here, I have the result that we got for the differential width and the width at maximum, and in this case, these indicators seem to work more or less well for all of the stars, so about half of the stars in all the bins seem to show a signal. And then finally, I have the result for the radial velocity here, and I just wanted to highlight that because radial velocity is not only an activity indicator, we also use that parameter to find planets, but in this case, at least in this sample, we've seen that the radial velocity is the parameter that shows the highest number of activity detection. So in a sense, it would be like the best tracer of activity that we have, which can be an issue because it's not only a tracer of activity, as you all know. So these are the results of the first project. I'm going to move on now to the second one. So the idea here was to take advantage of like this classification of activity indicators that we had to be able to perform an analysis, a line-by-line analysis and recompute velocities based on that. So the work here is heavily inspired by the work by Xavier and Miquel that you can see cited here. They have been mentioned a lot, so I'm just going to briefly talk you through the main idea. So the main idea behind this approach is that you take your spectrum and instead of computing a CCF over the whole spectral range or a template matching over the whole spectral range, you select your absorption lines, that's where your radial velocity information is, and compute a radial velocity for each of these lines. Then what you do with this radial velocity time series, you go line by line and look if there's a correlation between the radial velocity features the lines and an activity indicator. I have two examples here. So in this case, for this line that I've labeled as line number 1, you see that there's kind of a strong correlation between the velocity of this specific line and an activity indicator. So I would classify this line as active. And line number 2 here on the right, you see that there's the correlation, it's not strong. So in this case, I would classify this line as inactive. So we wanted to do this with some of the stars that we had observed with CARMENES. I'm mentioning CARMENES again because I'm using data from the GTO, and the GTO mostly focused on dwarfs, so that's the data that we had. And I wanted to highlight that because on purpose on the top here, I show before the spectra of G dwarfs. So this is like a CARMENES observation at a relatively high signal to noise ratio. You can clearly see some absorption lines here, and in the bottom plot here, I'm showing you same spectral range, but in this case, the star that was observed was mid-M dwarf. It's also CARMENES data, same wavelength range and similar signal to noise ratio, but in this case, you can see that the lines look quite more messy. It seems hard to like be able to isolate a single line. In most of the cases, like the minima that you can see here are actually blends. So I'm just going to put a big question mark here. Nevertheless, we wanted to apply this technique because we know that methods such as the CCF still work kind of well with M-dwarf stars. And what you do with the CCF, you basically have a mask where you have isolated your stellar lines, and this still works. We wanted to give it a go and try the line-by-line approach also with M-dwarf stars. So I'm showing again here results. The data that we used in this case is again YZCMI, this nice active star that shows a very clear activity signal at its rotation period. And I'm showing you again the same kind of plots as before. So the top panels here, where it says activity indicators, I'm just showing the time series of some of the activity indicators that we extracted from the spectra, so same ones as before. Above these ones, where I have labeled here all lines, I'm just showing you the radial velocity of the whole spectral range. So in this case, it's the radial velocity that we get from the cross-correlation function. And above this, the top plot here, I'm showing you the time series radial velocity of two specific lines. So we have isolated two of the lines and computed its radial velocities. Then what we did next is look at the correlation between these two lines and the different indicators that I have listed here. So that's what you can see in the small square plots here in the center, here in the right. I have the correlation between these indicators with the first line in these plots here on the middle, and here I've labeled that as line 1 here, and then the same thing, but for line 2 here on the center right and on the right here. And the first thing that we notice is that, again, some of the indicators tend to show correlations that look kind of linear, and in this case, these are the correlation with the total radial velocity, the bisector of the CCF, and the chromatic index. So we decided to first focus on these indicators because it was relatively easy to quantify the correlation, which is what we wanted to classify lines in active and inactive. And yes, this is what I'm showing here. So I've chosen these two lines on purpose to show that line number 1 here is what would be classified as an active line, because as you can see, it shows very clear correlations or anti-correlations with the 3 activity indicators here, and then line number 2 doesn't show anything clear, so this line would be classified as inactive. So yeah, we did this not for this only these 2 lines that I'm showing here, but for all the lines in the whole spectral range. So that's what I'm showing you here. So we just took all the lines in the spectrum, computed its velocity, computed its correlation with these 3 activity indicators, and here I'm showing you the correlation coefficient, the Pearson's correlation coefficient between the individual velocities of the lines here on the x-axis and the different indicators. So I have here the correlation coefficient with the velocities, with the bisector, and with the chromatic index. I wanted to show you this because we noticed that for the velocities, things are more or less correlated, so go from 0 to 1, and for the other 2 indicators, go from 0 to -1, so they show an anti-correlation, but the absolute value of the correlation is quite similar for the 3 indicators, so I've shown this here. So what you can see on the right-hand side is simply the correlation between these parameters here. So that would be the correlation of the Pearson's correlation coefficient. I apologize for that, but I hope you're following me. So the top left plot is simply the correlation between the bisector correlation coefficient and the real velocities. Below, the one with the chromatic index and real velocities, and then chromatic index and bisector. Just wanted to show you this because for these 3 activity indicators, all these things look very similar. So what we did next was, once we have this kind of classification in lines between active and inactive, we just went and selected different sets of lines and recomputed real velocities to see if the signals that we got related to activity changed there. So I'm showing you here an example. So we started with looking for inactive lines to see if the signal that we have due to the rotation of the star would decrease. So what you do here is you select lines that have a Pearson's correlation coefficient close to 0. So this like shaded region that I've highlighted here. And we also put a cut not only on the correlation coefficient, but also on the scatter of the line, because that's what I'm showing here. So I didn't mention that before, but on the y-axis here, I have the scatter of each line in time. So each line is a function of wavelength here. And we also put a cut on that because we noticed that you could have a correlation coefficient close to 0, but that didn't necessarily mean that that line was inactive. It could be that simply the line was in a noisy region of the spectra and then it showed no correlation with anything, or maybe it is like related to activity, but it doesn't show a linear correlation with the indicators that we were looking at. So we also discarded lines with high scatter. So we used 2 parameters to make our sets of lines. So that's what I'm showing here. On the y-axis here, I have the scatter of these lines, the different cuts that we put on the scatter of the lines, and on the x-axis, I have the scatter that we put on the correlation coefficient here, and the different points correspond to different sets of lines. So we just did this and recomputed the velocities of the whole time series of the star, and then looked at the scatter of the star, and that's what you can see in the colors. And you can see that for the initial sample of lines, so using all the lines with no cuts on the scatter of the lines and no cuts on the correlation coefficient, we had an initial scatter of about 90 meters per second, and by applying these different cuts and decreasing the number of lines that we have towards those that seem to be inactive, we get a scatter of about 20 meters per second. So it seems that we are actually decreasing the number of lines, which decreases the amount of information we have, but the scatter decreases. So it seems that we are effectively removing something that seems to be related to activity. So to check that, I wanted to show you the time series of these different real velocity data sets that we obtain for different lines, and also the periodograms that we obtain from this. So there's many things in this plot, but if you look at the top left here, I'm showing the time series velocity of the stars. So in black, it's the original ones that we got from the CCF using the whole spectral range, and then the different colors are different sets of lines. And I've written down the scatters that we get here, so we see that the scatter kind of decreases as we restrict the lines to those that seem to be inactive. And to further check that, we computed the periodogram. That's what you can see down here. I've just zoomed in the peak at the stellar rotation period, so you can see what's going on with the different data sets. And we see in black the original peak at the stellar rotation period, very strong, and we see that as we reduce the number of lines that we have, this peak seems to decrease. So it seems that indeed it's something related to the activity or the star or the scatter of the radial velocities. Yeah, and just to note, these are the results that we got using the correlation with the total radial velocity, but we got very similar things if instead we use the correlation of the bisector or the correlation with the chromatic index. And I just wanted to quickly show that the number of lines that we use here is very low. So we went from like 2,000 lines at the beginning, initially using like the whole spectral range, to only about 200 for the data set for which we obtained the smaller scatter, which seems good because like we seem to like remove the peak at the stellar rotation period, but again we are effectively discarding most of the spectra, which cannot be a good thing because we are like actually losing lots of information. So we just wanted to highlight that. And then I just wanted to clearly show we can do the same, but now for the active lines. So instead of lines with a correlation coefficient close to 0, you would go to lines that have a correlation coefficient close to 1 in the case of the velocities, or -1 for the other two indicators that were anti-correlated. And again, we see that in this case, the scatter increases because we have less lines and they seem to be active. I also wanted to highlight again that the number of lines that we end up using goes again from 2,000 to about 20 for the green data set here. And if you look at the periodogram of this data set, it's still like the peak at the stellar rotation period is very significant. It looks very similar to the periodogram in black. You can barely see that because it's just behind that. And we're just using 20 lines instead of the 2,000. So we just wanted to highlight that again, that the number of lines that we use is it's very, very small. And finally, I've just been showing you results for YZCMI. So that's like that star that was very nice, that showed this very clear activity signal. But we also did a comparison of these active and inactive lines for other stars. So I just wanted to quickly show you the comparison of these lines for YZCMI and another star, EVLAC. We also observed that with CARMENES, and they have a very similar spectral type, similar rotation, similar activity levels. And I wanted to highlight that here I'm just showing the correlation coefficient of the lines as a function of the wavelength for the two stars. So we did that for each star individually. And here I'm comparing in color, we have a data set of inactive lines for each of the two stars. Again, we did that separately for each star. And then the diamonds that I hope you can see here are the lines in these that we selected for each star to be inactive that are common in the two stars. And I just wanted to notice again that this is only like the inactive data set of each star had about 200 lines each, and the common ones are only 52. So I just wanted to show this to highlight that this seems to indicate that it might be difficult to find a set of inactive general lines to generalize for like general velocity pipeline. So we just wanted to point this out. And I see that I'm running out of time, so I'm just going to end here with a summary.
Thank you, Marina, for a very, very interesting talk. So any questions, Xavier?
Yes, thanks a lot, Marina. Can you hear me fine?
Yeah, I can.
Okay. So did you twice, or you are able to select, to see that some lines are much more affected by activity than others? Were you able to investigate further if those lines had some specific physical properties? I don't know, at depths, as like approximation, or like Landé factor, whatever. So on this side, or also on the shape of the line, that like morphology, most of the line. Were you able to go more into the depths of why some lines are affected and not some others?
Okay, I'm going to speak. I hope I'm muted. Yes, not with the M dwarf, because the lines there, it's like they're kind of messy. Most of them are molecular lines, so I started to do that, but it was kind of hard to classify which line was which, so I didn't really look into that. I did a bit of that with the Express stellar signal challenge that Lily talked about. I removed the slide that I had because I saw that I didn't have lots of time, but we did that with the stars that were in the challenge that were, I think, like G and K dwarfs. I'm not sure, they were not in dwarfs, and we didn't really see any relation with the active inactive lines and the depths and the lambda factors. It was like a very quick analysis, so I guess like it would need more time, but initially we didn't really find anything significant.
Thank you.
Any other questions? No questions? Annalise?
Hi, it was really interesting. This is not a question, but just an observation. I was intrigued by the fact that your correlations are very linear because your rotation period is 2.8 days, which should mean that the shift is only about 0.3 days in your case, and hence your correlation is stronger. So I was very much entertained by that.
Okay, all right, brilliant. If there are no other questions, then let's thank Marina again.